as far as we can. This is Unit 5. So this chapter is all of Unit 5. And then next chapter will be all of Unit 7. So that's like kind of crazy.
Does that mean we're done?
No, we still have Unit 8 and 9.
And those are the hard ones.
Yes. So
are we spending more time on these?
yes. So we are going to be spending a little bit more time on this stuff as we get further into it. What's possible? Who told you that? Oh, come on. It's not that bad. Aubrey Hemming? Okay.
Might have been more differently, but
Okay, so this chapter is kind of an intro chapter for the next one, but I think this chapter is actually pretty easy. So we are talking about chemical kinetics. When you hear the word kinetics, what do you think?
Motion.
Motion, yes. So this is the study of the speed or rate. So put rate in a box because that's the most important part of chemical reactions. And you might think, well, Heller, isn't it just fast, slow, medium? I mean, kind of, but there's lots of steps. So all chemical reactions occur at different rates. For example, rusting. Rusting is a very slow reaction, whereas an explosion would be very what? Fast. You got it. Would be very fast. A rate of reaction can be determined by monitoring the change or decrease in reactance. Oh, you're going to feel more like that in a day or so. Decrease in reactance over time, or the change or increase in products over time. Increase in products over time. So if I had the following equation, if I wrote out 2NO2 is in equilibrium, that's how you draw it. It's kind of a half arrow forward and a half arrow backwards. Equilibrium with 2NO plus O2. If I was going to make a graphical picture of what this would look like with reactants and products, here's how it would look. So here's my graph. I'm going to have concentration on my Y, and I'm going to have time on my X. Concentration and time. So you would agree that my NO and my O2 are both going to start at 0. Yes?
Yes.
So NO should go up, right? How much compared to O2?
Twice.
About twice as much, yeah. So here's NO, here's O2. Yes? Nothing too crazy yet. And then what's going to start up here? What am I going to actually start with? I'm going to start with some... The NO2, yes. The NO2. And the NO2 should go down about the same amount as what's going up.
Yeah.
About the same as what the NO is going up. So something like this. Something like that. That's actually if you look at that, that's pretty decent. If you look at that little space on the left, it's pretty good. Eventually, these will flatten out. And that shows you that my forward reaction and my backward reaction are the same because they're all parallel, yes? This is equilibrium.
that means very quick. We're constantly having products to reactants.
Correct. They're going both ways. That's really all we're going to talk about equilibrium for now. That's more next chapter. But that's just a nice little intro for you. So the basis of speed or rate is based on collision theory. So collision theory is all about, believe it or not, collisions. So collision theory tells us that a reaction will only take place if 3 conditions are met. Anybody want to guess what one of the conditions is? Don't overthink it.
They're colliding.
You got it. Number 1, the reactants come into contact with what?
Each other.
Yes. They come into contact with each other, aka they do what?
Collide.
They collide. So they have to run into each other. That's number one. Number two, what else has to happen in order for a reaction to occur? Think back to biology.
Substrate.
We are going to talk about substrates today.
What?
The collision occurs at a certain minimal energy called the what? Yes.
Oh. Is this bio?
Called the activation energy, yes.
Is this biochemistry?
No, not really, but it's related. And we're going to use for activation energy from now on E act. So capital E subscript act. Zoom out just a bit. Number three, the last thing, is the collision has correct molecular orientation. What does that mean? Okay, dot, 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 dot. What does that mean? That means that the reactants, I'll give you more, must collide in the correct 3D orientation. And don't freak out that there's going to be some kind of shapes or stuff you have to memorize, okay? They just have to hit the right way. It just has to hit right, you know? Just hit right. If reactants don't collide, if they don't collide or do not have an energy higher than the activation energy, guess what?
No reaction.
You got it. No reaction occurs. So, all reactions take place with a series of steps. Do you guys remember doing Hess's law? Where you had the 4 steps and you had to flip some, divide some by 2, get the energies.
The puzzle.
The puzzle one, yes. All right? So that's kind of what we're talking about. We're not going to be doing Hess's law, but that's what we're talking about here. So if you remember, if I have potential energy on my y and I have time on my x, it's going to look something like this. If I go here, I need to draw a little hump. There's my hump.
Is that activation?
Yes, and then go down to here. So here are my reactants. We already know what type of reaction this is. This will be what?
Exothermic.
Exothermic. These are my products. If I draw a line straight across here, between this and the hump is my what?
Activation.
That's my activation energy. So there's my EA. And then the difference between the reactants and the products is my what?
Delta T.
Not delta T. Delta H.
Oh,
Your enthalpy.
Why did I say delta T?
I don't know.
What's the difference? Okay, wait, question. So if it's all
I get it.
potential energy and you're converting it into like kinetic or a product, why wouldn't it go down to 0? Because there's no potential energy left.
Why doesn't it go down to 0? If it goes down to 0, then it would be like absolute 0. There's always energy in like the atmosphere.
Yeah, but isn't potential energy all being converted into kinetic energy?
Not all of it.
Okay.
Not all of it. That would be like a perfect world, right?
Ideal gas.
That would be like 100% yield.
Okay.
So these steps that we're talking about, these elementary steps, can fall into 3 categories or 3 molecularities. Molecularities. But all successful collisions are subject to the correct orientation. So this will give you a little more details, Jack, on what these are. So number 1 is called unimolecular or unimolecular.
1 molecule.
Yes, you got it. Unimolecular, so smart, is a single species reacts to form products. To form products when a rearrangement occurs. And we know that a rearrangement is also the same name for a chemical reaction. Remember Dalton's law? You need to memorize like chapter 1. This is considered first order. This would be first order. So this would be something like ozone.
Where is that for products?
When. Thank you. When a rearrangement occurs, that's first order. Ozone will break down into oxygen and also oxygen. It's really a weird reaction because that's O2 plus O.
A single what?
A single species reacts to form products when a rearrangement occurs. This is first order.
Is this,
So it's like the basic, most basic.
Yes.
would the 2NO2 yields NO plus O2 also be 1? Or is that?
That's not.
It's not.
Does that just be?
Because you can see how many things are there. There's 2. I have 2 NO2s, right?
Oh, singular.
So it literally has to be a singular.
How, are these very common?
What?
Like, no.
Okay.
She's asking if that's,
I'm just giving it, is what?
she's asking if like that's like,
Well, this is why it's really hard to break down ozone, right? You've got that ozone up there, and we're adding more ozone, yes, which is not good. Do you see a lot of single oxygens in life?
No.
No. So, not super popular.
Yeah.
The second one, anybody have a guess of what it is?
Die.
Bimolecular.
One of the two.
Bimolecular, molecular. Guess what this one is? 2 species colliding. 2 species colliding. So this would be your second order. Your second order. So this would be something like NO plus O3 yields NO2 plus O2. The reactions aren't important. These are just examples I threw out there. I don't even know if that's balanced. It's balanced. NO plus O3. NO plus O3 yields NO2 plus O2.
Oh, wait, no.
It's ozone.
Yeah, it is balanced.
Yep, it's balanced. And the third one's going to be trimolecular. Yes. Trimolecular. Guess which one of these is the most likely to happen? No.
bimolecular?
No. Unimolecular.
Wait,
Because remember, the less things involved, the more likely it's going to happen. Once you get up to 3 molecules, then you have to orient 3 molecules correctly
Oh.
to hit.
I thought you said it was the hardest to break.
Which one?
Like the
It's hardest to break up ozone.
Okay.
Well, I'm just saying, in general, this is difficult to do, but I'm saying it's more likely that you're going to break up 1 molecule than 2 or 3.
And do all reactions fall into one of these three categories?
Yes, you got it. So trimolecular is sometimes called termolecular. You might hear it called either one, which is 3 species colliding. 3 species colliding. So an example would be 2NO. Here it is. Well, this is actually a little different. Plus O2 yields. This is the reverse of what we did up top. Would you agree that there are 3 species on the left?
Yeah.
Because I have 2 plus 1. Yes? I got 2 plus 1.
Third order, or is that?
I mean, third order is not really something that we have to worry about too much. So, unimolecular, bimolecular, trimolecular. Oh, I got ahead of myself. I always do this. You can tell that I wrote these because, like, I just talked about the next paragraph.
Yeah, it's like,
Can I turn my page?
Yeah.
Okay.
Oh, wait.
I will drink water. This is day 2, clean.
Yeah.
Thank you. Day 2 off the dew. So, yes, day 2 without the dew. So, as I was saying, the less or the fewer molecules involved in the elementary reaction, the more likely it is that the collisions will be in the correct orientation. This means that increasing the molecularity, that's kind of fun to say. Molecularity, will decrease the chances of correctly oriented collisions. This is why trimolecular reactions are pretty rare. In all situations, if the concentration of the reactants is increased, there will be a greater chance of successful correct energy and also correct orientations of collisions. Why is increasing the concentration gonna make that more likely?
Just more.
There's more ions, right? Yes,
More likely that it'll hit in the right.
you got it. So if I have 1 molar hydrochloric acid or I have 12 molar, right? 12 molar hydrochloric acid is gonna have a much higher likelihood of reacting than 1.
Or you can have what we just accidentally calculated and have 24 molar hydrochloric acid.
Or 24, yes.
I don't think that's
Once you string a series of these together, it becomes more complicated. But the more complex reaction is just a series of simple ones, which we call elementary steps. So we're going to be doing a lot with these steps, and it's actually super easy.
Wait, what does it say before the and of the top line? Like the successful parentheses correct something incorrect.
Correct energy orientations. So the big thing that we're going to be starting to talk about is this intermediate. I'm going to start talking about this intermediate. Do you guys talk about that in biology? Okay. So there's this intermediate step. So here's my reactants. Well, all we see is reactants and products. There's this intermediate step that we never see. Guess why?
Oh, is it like, it's gotta like cycle back around?
Well, it's so fast, right?
Yeah.
So there's this intermediate step, but we don't see it because it's like less than a second. But it happens.
what is it?
Flip the page. So, factors influencing reaction rates. So the first one we just talked about was concentration. So this is the first way I can increase my reaction rate because we said increasing the reactants. Someone's got to keep track of the time because I have no idea when this is over. Comma, increasing the reactants concentration will increase collisions, increase the frequency of collisions. Number 2, temperature, right? What is this a picture of?
Looks like the distribution.
The Maxwell-Boltzmann? Yes. Once again, it's back. This is the Maxwell-Boltzmann distribution. So I feel like it's kind of hard to see like on this picture, so I'm going to draw it again down here. So here's my graph.
You want us to also do it?
Yes, I do. Here's the number of particles on my y. Here's my energy of particles on the x. Here's my energy of particles on the x. So here's my start at a lower temperature, right? So here is my activation energy right here. It's tiny, but that's my activation energy. If I increase it, what happens to my hump? My hump gets
Increase temperature?
lower into the
It evens out.
right, correct? Because it's the same area. Remember the number of particles in here is the same area?
Is that energy particles on the X?
Yes, energy of the particles. So now, look how many more particles I have at my activation energy now. I've got way more. I've got way more at the activation energy. So this is the activation energy I need to get it to. Now I have a lot more here than I did before. Yes, I can. Does that make sense?
Why is the activation energy not shifted off to the left? Because technically, wouldn't that be?
Well, my activation energy is not changing. I'm saying like this. Let's say that's a number of joules. That's the energy you have to get it past.
Oh, okay.
So at a colder temperature, I have less particles at that temperature. Once I heat it up, I've got all those at a higher temperature. So the activation energy doesn't change. I just have more particles at that energy. Okay? So concentration, temperature, down here, number 3. What else? What about particle size? Well, this solid particle side.
Oh,
If it's a solid, I have to do what to my surface area? Increase the surface area. Yes. Increase my surface area. That's 3. There's only one other way I can do this. So I can increase the concentration. I can increase the temperature. I can increase the surface area.
It's like pressure or something?
Not pressure. Not volume.
Where is it?
Think back to biology.
Catalyst.
Catalyst.
Oh.
You got it. Can I flip my page?
You were at the other page, didn't you, Megan?
I don't know.
Number 4 is use a catalyst.
Is that like fire or something?
Heat. It could be, yeah, fire is heat. All right, so catalysts are substances that increase the rate of reaction while remaining chemically unchanged. We're going to talk about what chemically unchanged means in a second. Well, probably tomorrow. Catalysts lower the what?
Activation.
Yes, they lower the activation energy. This does not change the heat of enthalpy. It does not change the heat of enthalpy. My reactants and products are still going to end at the same spot, right? It just lowers this hump. So that's what this picture is showing. The heat of enthalpy is not changing. More specifically, catalysts cause more effective collisions. More effective collisions and or provide a reaction path with a lower activation energy.
Acid base, I don't know.
So, types of catalysts. Don't worry about this, all right? Acid base is the first one where a reactant will either lose or gain a what? When you're talking about acids and bases, not an electron,
pH?
a proton.
Is it hydrogen?
It's a hydrogen atom, but that's essentially a proton, right? Because a hydrogen only has one proton. Forming a new intermediate. Forming a new intermediate. So as a result, the reaction has changed. In a reaction mechanism containing a catalyst, the concentration of the catalyst is unchanged. Yes, I can. So sorry. Is unchanged.
What are the 2 brackets?
Concentration. Concentration is, that's always my,
Concentration right after.
yes,
Yeah, but like it's
the concentration.
that would be concentration.
I'm just saying the concentration. Here,
It's not a big deal.
here we go. Now are we happy? Okay. Is unchanged. However, the catalyst will sometimes be consumed in the rate determining step. We're going to come back to that tomorrow. I'll tell you tomorrow. Only to be reformed in a later step in the mechanism. So, we'll stop there. So the thing is that catalysts are used and then reformed. So what you're going to find out about a catalyst, if you start with it, you end with it. That's how you determine what a catalyst is. It's super easy. That is all the time we got.